extracted from its ore by any method is generally impure and is known as crude metal. The impure metal is purified by subjecting it to a process of purification or refining. If electrolysis is used to purify or refine the metal, the process is called Electro Refining. Hence, Electro Refining is defined as the process by which an impure metal is purified electrolytically to obtain a pure metal. In this method of purification by electrolysis, the impure metal is cast into a slab and used as the anode, while a strip of the same metal in its pure form is used as the cathode. An aqueous solution containing a soluble salt of the same metal is used as the electrolyte. Then, both electrodes are immersed in the electrolyte to complete the electro refining setup. When electricity is passed through this setup, pure metal is deposited on the cathode. The more basic impurities in the impure metal go into the electrolyte solution, while the insoluble impurities, particularly the less basic ones, settle at the bottom of the electrolyte as anode mud. Let us look at the process of electrolytic refining copper to understand this further. In this process, impure copper metal is cast into the anode, while a thin strip of pure copper strip is made into the cathode. An acidified solution of copper sulfate is taken as the electrolyte. Next, the power is switched on. Observe the electrodes and electrolyte. You will observe that the size of the cathode strip increases as a result of the deposition of pure copper metal on it. At the same time, the size of the anode decreases as a result of the consumption of impure copper. Some impurities are also deposited in the electrolyte. Let us try to understand the mechanism involved in this electrolysis. Aqueous copper sulfate solution consists of copper plus 2 and hydrogen cations and hydroxide and sulfate anions. When electricity is passed through this, the copper atom oxidizes to copper plus 2 ions at anode. These copper ions enter into the aqueous solution, so the anode decreases in mass. Next, these copper plus 2 ions in the aqueous solution migrate towards the cathode and discharge there. Thus, pure copper is deposited at the cathode. The more electropositive impurities like iron, nickel, and zinc ionize and are left in the electrolyte as their sulfates, while the less electropositive impurities like gold, silver, and antimony are insoluble, so they settle at the bottom of the electrolyte as anode mud or slime. Interestingly, precious metals like gold and silver can be later recovered from the anode mud. Besides copper, other metals like silver, zinc, and lead are also purified by this method. In general, highly electropositive metals are purified by electrolysis. Acids, bases, and salts conduct electricity in their aqueous and molten states. Let us perform an experiment to understand their conductivity. Place 2 beakers on a table. Pour some dilute hydrochloric acid into the first beaker. Next, pour some acetic acid solution into the second beaker. After filling the beakers, dip 2 graphite rods in each. Connect wires to the graphite rods in the beakers. Then, connect batteries along with a switch to these wires to complete the circuit for in each beaker. Insert an electric bulb in each circuit. Ensure that all connections in both the circuits are proper. Turn on the switch to allow the circuit in the first beaker to complete and observe the bulb. At the same time, turn on the switch that completes the circuit in the second beaker and observe the bulb. Compare the intensities of light emitted by both bulbs. You will see that the first bulb glows bright, whereas the second bulb is dim. Based on these observations, we can say that the two solutions, hydrochloric acid and acetic acid, are electrolytes, but there is a difference in their electrical conductivity. This variable conductivity can be explained based on their degree of dissociation. The degree of dissociation is more in hydrochloric acid and less in acetic acid. Hydrochloric acid, when dissolved in water, dissociates completely into hydrogen and chloride ions. These ions are more in number and they have high mobility, which leads to high conductivity in hydrochloric acid. Hence, hydrochloric acid is considered as a strong electrolyte. On the other hand, acetic acid decomposes partially in its aqueous solution, so the number of mobile ions is less. Therefore, it has a lower conductivity. So, acetic acid is a weak electrolyte. Another example of a strong electrolyte is nitric acid. It gives hydrogen and nitrate ions in its aqueous solution. Likewise, sulfuric acid dissociates into hydrogen and sulfate ions when dissolved in water, and it is also a strong electrolyte. Formic acid, on the other hand, dissociates into hydrogen and formate ions, but the extent of dissociation is very less. Hence, it is a weak electrolyte. Carbonic acid is another example of a weak electrolyte. The same principles are applicable to bases and salt solutions for categorizing them as strong or weak electrolytes. For instance, sodium hydroxide, potassium hydroxide, and lithium hydroxide are strong bases and they act as strong electrolytes. On the other hand, weak bases such as calcium hydroxide, ammonium hydroxide, and magnesium hydroxide are weak electrolytes. Salts like lead bromide, copper chloride, and silver nitrate dissociate completely, so they act as strong electrolytes. Whereas sodium carbonate, potassium bicarbonate, and lead acetate are weak electrolytes, as the extent of dissociation is less in their solutions. Thus, based on the degree of dissociation, electrolytes are classified as strong electrolytes or weak electrolytes.
You will need to be careful not to get water on this bracelet. The gold plating might wear off.
Oh, you mean it is not real gold?
No, for custom jewelry, the pieces are generally made from copper and then coated with a layer of gold.
I always wondered how you managed to get a uniform layer of gold on pieces of such varied shapes and sizes.
We employ chemical effects of electricity to do this. The process of coating jewelry, in specific, is called electroplating.
In this lesson, you will learn about the chemical effects of electric current and electroplating. At the end of this lesson, you will be able to identify the chemical effects of electric current, demonstrate the chemical effects of electric current, describe the steps in the process of electroplating, and list the uses of electroplating.
When an electric current is passed through a conducting solution, it causes chemical reactions that can lead to formation of gas bubbles at the electrodes, deposit of a layer of metallic coating on the electrodes, or change in the color of the solution. Electroplating is the process of depositing a layer of any desired metal on another metal using electric current. It is the most common application of chemical effects of electric current.
Interesting how electricity can be used to create such beautiful objects. Jean, listen to this. In 1800, a British chemist, William Nicholson, had shown that if electrodes were immersed in water and a current was passed, bubbles of oxygen and hydrogen were produced. Oxygen bubbles formed on the electrode connected to the positive terminal of the battery, and hydrogen bubbles formed on the other electrode. Can we verify this at home?
Let me see. Sure, we can try this out. Let's get the apparatus for an experiment first. We need 2 conducting wires, a battery to connect to the wires, 2 electrodes such as carbon rods, and a conducting solution in a glass trough. I think we can use a common salt solution. Okay. So, to demonstrate chemical effects of electric current, we need to first wind the free ends of the 2 wires around the head of each carbon rod to make a contact between the carbon rods and the wires. Connect the other free ends of the 2 wires to the battery. One to the positive terminal and the other to the negative terminal of the battery. Then, immerse the carbon electrodes in the conducting solution and keep them undisturbed for about 5 minutes.
Oh look! There are gas bubbles forming at the surface of the carbon rods. But Jean, there seems to be no change in the color of solution or the carbon rods.
Well, I guess that's because the chemical reaction depends on what solution and electrodes are used. Let's repeat the experiment, replacing the carbon rods with a copper strip and an iron nail as electrodes dipped in a container having copper sulfate solution. Now, you will witness a change in color. With this solution, you should be able to see the coating effect used for electroplating. You need to give some time for the process to take place.
Yes, the color of the solution has changed. From blue, it has gone green.
Right. That's because of the chemical reaction in the solution. Simultaneously, as you can see, a deposit of copper takes place on the electrode connected to the negative terminal of the battery. So, the iron nail on this terminal has got a coppery tint now.
Mr. Welch at the jewellery shop was saying that electroplating is the one of the common applications of chemical effects of electric current.
Yes. It is used primarily for coating objects with other material.
I can see how passing an electric current through a solution helps deposit a layer of a metal on an object. But I'm not sure what actually happens in the solution.
Let's try to resolve this confusion. We used a copper strip and an iron nail in copper sulfate solution. Let's see what happens if we replace the iron nail with another copper strip. Take out the strips out of the solution and see. What do you observe?
I can see that one copper strip is slightly brighter than the other.
Yes, that's what would generally happen. When an electric current is passed through the copper sulfate solution, copper sulfate dissociates into positive copper ions and negative sulfate ions. The copper ions, being positively charged, move to the electrode connected to the negative terminal of the battery, absorb electrons from the electrode, and convert into copper atoms. The copper atoms get deposited onto the copper strip connected to the negative terminal of the battery.
But what about the loss of copper from the solution? Doesn't that make the solution unstable?
Well, not really. From the other copper electrode, which is connected to the positive terminal of the battery, an equal amount of copper gets dissolved in the solution due to reverse chemical reaction. As copper gets transferred from one electrode to the other, the loss of copper from the conducting solution is compensated for, and the process continues.
And this transfer leads to the coating on one of the copper strips.
Absolutely correct. It is because of this coating that the copper strip connected to the negative terminal appears slightly brighter.
Jean, all this gold-plated jewelry looks beautiful, right?
Yes. It looks as though it is made of gold. You have to thank technology for that.
Actually, if you look around, jewelry is not the only industry electroplating is used in.
He's right. It is widely used in manufacturing industry for coating metal objects with a thin layer of a different metal that has a desired property. For example, industrial machines are coated to avoid chemical reaction with raw materials. Metal food containers are made of iron and electroplated with tin. Tin prevents food from reacting with iron and protects it from being spoiled. Can you think of other items around you that have a coating of some other metal?
I guess my bicycle handle. I scratched it last week and I could see the shine had disappeared from that portion.
That's right. Your bicycle handle and wheel rims are coated with nickel to give a shiny look. Chromium and nickel resists scratches and corrosion. Therefore, they can be used in electroplating to prevent corrosion due to wear and tear of objects. But chromium is expensive. So, mostly nickel is used as electroplating material to prevent corrosion. Due to this property, chromium and nickel are also used for electroplating bath taps.
Another application of electroplating is found in the reinforcement iron bars used in construction of buildings and manufacture of cars. These iron bars are electroplated with zinc to protect them against corrosion and formation of rust.
Wow! I didn't realize there are so many applications of electroplating that we use in our daily lives.
Right. Electroplating is also used for coating electronic components to make them resistant to heat.
There is a flip side to the use of this technology though. In the industries that take up electroplating, the disposal of the used conducting solution has become a major concern. It is a polluting waste.
Oh, so how do we protect the environment?
There are specific disposal guidelines to protect the environment. We are very careful about following those guidelines here. So, not to worry.
This brings you to the end of this lesson on chemical effect of electric current. In this lesson, you learned to identify the chemical effects of electric current, demonstrate the chemical effects of electric current, describe the steps in the process of electroplating, and list the uses of electroplating. An electrolytic cell is an arrangement in which an external source of voltage brings about a chemical change. Since electrical energy is put in, the reaction is non-spontaneous. When you recharge a battery, you are actually running them as electrolytic cells. Let's look at a simple electrolytic cell. As shown in the diagram here, it consists of two copper electrodes immersed in an aqueous copper sulfate solution. The electrodes are connected to a DC power supply. When the power supply is turned on, reduction occurs at the cathode, which is the electrode connected to the negative lead of the power supply. Oxidation occurs at the anode, which is connected to the positive lead of the power supply. The reduction half reaction at the cathode has copper 2 ions gaining 2 electrons to form metallic copper. At the anode, copper metal undergoes oxidation by losing 2 electrons to form copper 2 ions. Students often find it difficult to remember the difference between galvanic and electrolytic cells. In galvanic cells, the anode is considered to be the negative electrode, and reactions are spontaneous. The cell potential is always positive, and the change in Gibbs free energy is negative. In electrolytic cells, the cathode is considered to be the negative electrode, and the reactions are non-spontaneous. The cell potential is negative, and the change in Gibbs free energy is positive. Remember, in any cell, oxidation occurs at the anode and reduction occurs at the cathode. For example, an impure sample of copper can be used as the anode. As the cell runs, pure copper is deposited on the cathode. Less reactive metals such as silver and gold and non-reactive impurities fall to the bottom as anode sludge. Similar processes are used to produce sodium, magnesium, aluminium, and other metals on large scales. Michael Faraday was the first scientist to quantitatively study electrolysis. Faraday's work can be summarized in his 2 laws of electrolysis. Faraday's first law states that the extent of chemical reaction that occurs at any electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. The electrolyte may be molten or in an aqueous solution. In other words, the mass of an element that deposits at an electrode during electrolysis is proportional to Q, the total amount of electricity passed through the cell. Faraday's second law states that the amounts of different substances produced by the same amount of electricity passing through the electrolytic solution are proportional to their equivalent masses. Equivalent mass can be calculated by dividing the atomic mass of a metal by the number of electrons needed to reduce a cation. The amount of charge Q passed through the cell can be determined from the product of current and time. To determine the charge in coulombs, multiply the current in amperes by the number of seconds for which it was applied. The stoichiometry of the half reaction needs to be considered in quantitative electrolysis. The half reaction relates the number of electrons to the metal deposited. For example, in the reduction of silver ions, 1 mole of electrons is needed for each mole of silver ions that reduce. You know that the charge on one electron is equal to 1.6021 multiplied by 10 raised to the power of minus 19 coulomb. Hence, the charge on 1 mole of electron is equal to the product of the charge on an electron and the Avogadro number. This can be written as the product of 1.6021 multiplied by 10 raised to the power of minus 19 and 6.02 multiplied by 10 raised to the power of 23. Therefore, the charge on 1 mole of electrons is equal to 96,487 coulombs per mole. This quantity of electricity is called Faraday, which is symbolized by capital F. Sometimes, this is rounded off to 96,500 coulombs per mole of electrons. Now use all this information you just learned to solve a problem. A 2.50 ampere current is passed through molten magnesium chloride for 15.0 minutes. What is the mass of magnesium deposited at the cathode? Let's work through this problem together. First, we'll find the charge that passed through the cell. You know that charge in coulombs is equal to the current in amperes multiplied by the time in seconds. We need to convert 15.0 minutes into seconds. 15 minutes into 60 seconds per minute is equal to 900 seconds. The current is 2.50 amperes. The charge that passed through the cell is then 900 seconds times 2.50 amperes, which is equal to 2,250 coulombs. From the half reaction, we see that 2 moles of electrons are needed for each mole of magnesium atoms that form. Therefore, we require 2 Faradays, or 2 multiplied by 96,487 coulombs, to deposit 1 mole or 24 grams of magnesium. Therefore, for 2,250 coulombs, the mass of magnesium deposited is equal to 24 grams per mole multiplied by 2,250 coulombs divided by 2 multiplied by 96,487. Thus, 0.2798 grams of magnesium is deposited at the cathode.